Imagine yourself suspended in the vastness of the ocean, sunlight filtering down from the surface above. And as you drift, you begin to feel a subtle yet persistent current tugging at you, gently guiding you along a path you didn't choose. You can't see it, this invisible force, but you feel its power, its unwavering direction. It's a mysterious flow, a hidden river within the sea. Now take that feeling, that sense of being moved by something unseen, and picture something similar happening, not in the familiar waters of our planet, but to our entire universe. Scientists, peering into the deepest reaches of space, have noticed a peculiar phenomenon. They've observed that massive groups of galaxies, clustered together like islands in a cosmic sea, are not simply floating randomly. Instead, these colossal structures might be drifting together, seemingly pulled by something truly enormous, something completely invisible to our instruments. It's as if they're all caught in the same cosmic current. To picture this vast and complex idea, imagine the universe as a dark room stretching out infinitely in all directions, filled with countless balloons, each one representing a galaxy cluster, a collection of hundreds or even thousands of galaxies, bound together by gravity. After the Big Bang, the event that birthed our universe, all these balloons started drifting apart, propelled by the initial expansion. This expansion continues to this day, pushing everything further and further away from everything else. But what if, amidst this general expansion, you observed a significant bunch of balloons moving together, all heading in roughly the same direction? What if it appeared as if an invisible fan, far larger than anything you could comprehend, was blowing them all in unison, creating a coordinated flow? That's precisely what some scientists believe they found evidence for in the distribution and movement of galaxies across the cosmos. They call this mysterious shared movement the dark flow, a term that hints at its enigmatic nature and unknown origin. Hundreds of galaxy clusters, scattered across an immense expanse of space, billions of light years in diameter, all seem to be collectively moving toward a specific, relatively small patch of sky, as if drawn by an unseen force. This discovery is profoundly surprising because one of the fundamental assumptions of modern cosmology is that the universe, on a large scale, is supposed to look the same in every direction. There shouldn't be any special direction, no cosmic downstream that everything is flowing towards. The combined gravitational pull from all the visible matter in the universe, all the galaxies and clusters we can see, simply isn't strong enough to explain this powerful and coherent current. This suggests that something far more massive, something hidden and unseen, lies beyond the edge of our observable universe, exerting its gravitational influence on everything within our cosmic horizon. The dark flow, if confirmed, could be a tantalizing clue, a cosmic breadcrumb leading us to the profound realization that the cosmos is even bigger, even stranger, and far more interconnected than we have ever dared to imagine. It opens up the possibility of realms beyond our current understanding, challenging our fundamental assumptions about the nature of reality itself. The universe is a vast and mysterious place filled with wonders we are only beginning to understand. One of the most intriguing discoveries in recent years is the existence of a massive invisible current pulling galaxies across billions of light years. But how did scientists spot this invisible current? What tools and techniques did they use to unveil this hidden force shaping the cosmos? They used the cosmic microwave background, or CMB, the universe's oldest light. This afterglow of the Big Bang provides a unique window into the early universe and serves as a backdrop against which we can measure the motion of cosmic structures. Think of the CMB as a baby picture of the universe, capturing a moment when the cosmos was just a few 100,000 years old. It's a relic of a time when the universe was a hot, dense plasma, and the light emitted then has been traveling across space ever since. This ancient light appears as a faint glow that's almost the same temperature everywhere. However, subtle variations in this temperature hold valuable information about the structure and motion of the universe. As galaxy clusters move through space, they interact with this background radiation. This interaction causes them to slightly change the CMB's temperature in their direction, a subtle but measurable effect. These temperature shifts are incredibly small, but they provide a crucial clue to understanding the movement of these massive structures. It's like a car driving through rain, making the drops hit the windshield harder. The faster the car moves, the more forceful the impact of the raindrops. By measuring these tiny temperature shifts in the CMB, astronomers could track the speed and direction of these cosmic cars, clusters millions of light-years away. This allows them to map the large-scale movements of matter in the universe. This effect, called the kinematic Sunyaev-Zeldovich effect, is a powerful tool for studying the dynamics of the cosmos. In essence, it acts like a cosmic speedometer, allowing us to measure the velocities of distant objects relative to the CMB. When astronomers analyzed hundreds of clusters, using data from various telescopes and surveys, they found many moving together, not randomly, but in a coordinated fashion. These clusters were hurtling through space at over 2 million miles per hour, an astonishing speed on a cosmic scale. And their movement wasn't random, they were all heading toward a specific spot in the sky, located between the constellations Centaurus and Vela. This wasn't just a local current, it wasn't just a few galaxies moving together in a small region of space. It stretched across a huge part of the observable universe, indicating a truly colossal structure at play. The discovery sparked debate and excitement as scientists grappled with the implications of this massive flow across the scientific community, leading to new research and investigations into the nature of this cosmic phenomenon. If the dark flow is real, what could be pulling so many galaxy clusters at once? One idea, gigantic structures like superclusters or massive black holes just beyond our observable universe, whose gravity reaches us even though we can't see them. Another theory, the pull comes from a neighboring universe in a multiverse with its gravity leaking into ours. Or maybe our understanding of gravity itself is incomplete. Perhaps gravity behaves differently on cosmic scales, creating these flows. Each theory is wild, pushing the limits of what we know about reality. Right now, we don't have enough evidence to choose between them. Solving this mystery could change our understanding of the universe forever. The concept of the dark flow, this mysterious, coherent movement of galaxy clusters across vast cosmic distances, certainly captures the imagination. It hints at something beyond our current understanding of the universe, something tugging at the fabric of space itself. But as exciting as the dark flow is, science demands strong evidence, rigorous testing, and perhaps most importantly, consensus within the scientific community. And right now, the community is divided on whether the dark flow is a genuine phenomenon or simply a statistical anomaly. Some teams, poring over data from various sources, have indeed found evidence supporting the effect, identifying a consistent direction of motion that seems to defy conventional explanations. But others, employing different methods, refining their analytical techniques, and leveraging what they believe to be better, more comprehensive data sets, see only random motion, the kind of statistical fluctuations one would expect in a universe governed by the standard cosmological model. They argue that the apparent flow is nothing more than a chance alignment of galaxies. Measuring these tiny shifts, these subtle deviations in the velocities of distant galaxy clusters, is incredibly hard, pushing the limits of our observational capabilities. And interference, whether from atmospheric effects, instrumental errors, or even stray electromagnetic radiation, can easily create false signals, mimicking the appearance of a real effect where none exists. Newer telescopes equipped with state-of-the-art sensors and designed to minimize systematic errors like the Planck satellite, which meticulously mapped the cosmic microwave background, haven't found strong, statistically significant evidence to corroborate the existence of the dark flow, casting further doubt on the initial claims. The data, in their view, simply isn't there. This lack of independent confirmation from multiple sources is a key reason why many in the astronomical community remain skeptical, leading many to doubt it's real. Still, the original team, convinced of the validity of their methods and the robustness of their findings, stands by their results and continues to refine their analysis, explore new data sets, and search for better, more compelling evidence to support their controversial hypothesis. This ongoing debate, this clash of interpretations and methodologies, is science in action, a perfect illustration of how the scientific process works. It's about proposing bold ideas, subjecting them to tough tests, and engaging in constant questioning, all within the framework of peer review and open discussion. Whether the dark flow ultimately proves to be a real phenomenon, a glimpse into a hidden sector of the universe, or simply a statistical fluke, the very act of searching for it, of trying to unravel this cosmic mystery, pushes us to build better tools, develop more sophisticated techniques, and fundamentally rethink what we know, or think we know, about the structure and evolution of the cosmos. The universe, in its vastness and complexity, is full of mysteries, puzzles that challenge our understanding and beckon us to explore further, and that inherent sense of wonder, that insatiable curiosity, is the best reason to keep exploring, to keep pushing the boundaries of human knowledge, and to keep searching for answers to the universe's deepest secrets.